Good afternoon. In this session, we'll unpack NVIDIA GAUGAN's architecture and its implications for AI-driven image synthesis. GAUGAN uses AI to convert rough sketches into detailed images, acting like a painting assistant that infers color, texture, and form from simple lines. We'll outline the core ideas, survey the system's building blocks, and discuss why these decisions matter for AI-driven image creation. By the end, you'll have a clear map of the essential concepts behind GAUGAN and their relevance to researchers, artists, and designers. Today, we'll take you through GAUGAN from the ground up. We'll cover the core concepts that let simple drawings become realistic scenes, then peek under the hood at GAUGAN's architecture, the design that ties ideas to code. We'll explain semantic segmentation, how the system learns to label parts of a scene like sky, water, and trees so it can render them correctly. You'll learn about the input generator, the signals that start the image creation, and then dive into the network details, the building blocks and how they learn, plus how the discriminator acts as a judge to steer improvements. We'll look at the user interaction and interface, showing how you'll actually use the tool and what the controls feel like. Finally, we'll discuss advantages and limitations, real-world applications and impact, and wrap up with a look at future directions. Next, we zoom in on GAUGAN, NVIDIA's smart image tool that turns rough sketches into photoreal landscapes. You label sky, water, trees, and the AI fills in color, texture, and lighting in real time. At its heart is a generative adversarial network, two subnetworks pushing each other toward realism. We'll see how this semantic image generation speeds concept art, game levels, VR environments, and teaching aids while keeping humans in the loop to steer results and guard ethics. Then, we preview milestones, GAUGAN's 2019 release, spade normalization, GAUGAN 2 with multimodal synthesis, and faster real-time generation, plus the shift from doodles to detailed scenes. We'll also discuss practical uses in design studios, classrooms, and film divided by advertising, and how artists and developers collaborate with the tool to prototype ideas quickly. Finally, we'll glance at future directions, more styles, more control, and broader accessibility. Building on the capabilities of GAUGAN as a real-time, semantically guided image synthesis tool, I want to drill into some of the advanced ideas that researchers are using to push reliability, realism, and availability further. These are not just engineering details. They shape how we design, compare, and extend these systems in professional settings. First, stability and fidelity through regularization. Modern high-resolution GANs benefit from spectral normalization in the discriminator, which constrains the spectral norm of each layer and helps stabilize training across diverse textures and lighting regimes. Gradient penalties, most notably the ideas behind WGA and GP, enforce smoothness in the critic's response, reducing training artifacts at region boundaries and across complex semantic layouts. When you label sky, water, trees, and terrain, these regularizations help the network learn coherent transitions rather than abrupt, visually jarring changes. The result is more reliable rendering of gradual lighting falloff, subtle reflections, and natural texturing that scales from rough sketches to photorealistic details. Second, robust evaluation beyond subjective recall. While FID, Frechet inception distance, remains a practical proxy for photorealism, it benefits from complementary metrics. LP-IPS, Learned Perceptual Image Patch Similarity, captures perceptual differences that correlate with human judgments of texture and structure, while SSIM and PSNR provide signal to noise and structural fidelity checks. Pairing these with user studies where designers rate realism, coherence with semantic maps, and ease of use yields a more nuanced assessment of a tool's practical value. For researchers, ablation studies that quantify how changes in losses, normalization strategies, or conditioning layers affect FID and LPAPS are especially informative. Third, hybrid and conditioning-driven approaches. Beyond vanilla GANs, diffusion GAN hybrids and diffusion-inspired refinement can enhance global coherence while preserving the speed and controllability of GANs. Conditioning mechanisms like SPADE, spatially adaptive normalization, enable fine-grained, region-specific color and texture control conditioned on the semantic map, producing more faithful scene elements such as foliage density or cloud formation. Hybrid models may use a fast GAN pass for core structure, followed by a diffusion-based pass for texture, fidelity, and weather effects, offering a practical balance between interactivity and detail. Finally, the human in the loop and safety considerations. Real-time design tools are most useful when humans retain final interpretive authority. Clear labeling of AI-generated suggestions, editable semantic maps, and intuitive controls for weather, lighting, and time of day help manage expectations and prevent misrepresentation. Ethical use and transparency remain central as these systems scale to more diverse styles and contexts. GAUGAN marks a clear inflection point in how researchers think about translating sketches into photorealistic imagery. Beyond the idea of a sketch-to-image demo, the work embodies a carefully engineered system where structure and texture are learned to cohere under semantic guidance. The spade normalization at the core of GAUGAN keeps the scene's layout intact while allowing textures to strike the right balance between realism and variety. In practice, this means the generator uses a semantic map as a conditioning signal that shapes where trees belong, where water should reflect, and where cloud should drift without letting texture synthesis drown the scene's underlying geometry. From a technical perspective, the stability and quality of these generators rely on techniques that researchers now consider essential for high-fidelity image synthesis. Spectral normalization constrains the discriminator's weight spectrum, helping to stabilize training and curb the tendency of networks to explode or collapse during adversarial optimization. Gradient penalties, such as those used in Wasserstein-Gann-style objectives, enforce a smooth Lipschitz constraint and encourage meaningful gradient flow when the generator explores the space of plausible textures. Together, they reduce training instability and sharpen details in the final outputs, which matters when you are converting rough lines into convincing landscapes. Advancing GAUGAN to GAUGAN 2 introduced multimodal synthesis, enabling inputs beyond sketches to guide results. This shift illustrates a broader theme in modern generation, fusing multiple modalities, spatial sketches, color hints, and natural language prompts to constrain and enrich the output. The fusion is typically realized through dedicated conditioning pathways and learning-based fusion modules that align different input channels into a coherent latent representation. Real-time feedback becomes feasible because these components are designed for fast inference, enabling researchers and artists to iterate rapidly and assess how different cues reshape composition, texture, and tone. Evaluating progress in this space goes beyond looking pretty pictures. We now rely on metrics like Fréchet inception distance, which quantifies how close the distribution of generated images is to real ones in a learned feature space, and perceptual measures that capture texture, fidelity, and structural similarity. Ablation studies and human judgments help reveal how well the model preserves scene semantics while delivering photographic realism. These rigorous assessments are essential when comparing hybrid or progressive architectures and when guiding future improvements. Ultimately, GAUGAN's trajectory, integrating semantic control, stability techniques, multimodal inputs, and real-time performance points toward a family of hybrid models that blend the strengths of GANs with diffusion-inspired refinement or VAE-like latency savings. The result is not only faster tools for studios and classrooms, but a framework for rigorous exploration of how machines learn to see, interpret, and paint the world from sketches into science, art, and pedagogy. Let me expand on how GAUGAN can transform creative practice, not as a novelty, but as a rigorously useful tool for researchers, designers, and producers. Beyond turning a rough doodle into a believable scene, the technology now sits at the intersection of fast iteration and measurable quality, precisely what teams need in art, games, film, and education. From a technical standpoint, real-time workflows benefit from advances in stabilizing GAN training. Spectral normalization on the discriminator helps constrain its gradients, allowing higher capacity critics without amplifying artifacts. Gradient penalties, such as those used in WGA and GP, further enforce smooth mappings from semantic inputs to image space, reducing instability during rapid in-workshop adjustments. When combined with perceptual or style losses that align textures, lighting, and climate cues with human judgment, GAUGAN style systems produce outputs that feel coherent over a sequence of iterative refinements. Evaluating these outputs goes beyond eye-test impressions. Researchers increasingly rely on quantitative metrics to compare design variants and track progress. Fréchet inception distance (FID) provides a global sense of how close the generated landscapes are to real references, while LPIPS perceptual similarity captures fine-grained texture and mood differences. Complementary metrics, edge, and texture-focused measures, structural similarity indices, and even task-driven evaluations (e.g. how well generated scenes support navigation or gameplay tasks help establish reliability. In practice, we pair these with user studies and ablation analysis, ensuring that improvements in scores align with perceived quality and utility. Architecturally, there is room for hybridization and refinement. Patch-based or multi-scale discriminators can better capture texture, weathering, and material boundaries. Conditioning can extend beyond semantic maps to depth, sun position, weather, and time of day, enabling controlled, physically plausible variations. Looking ahead, hybrid models that combine GANs with diffusion processes or VAE-based components promise to blend sharp, diverse details with stable, controllable generation. Such hybrids can offer faster local sampling for rapid iteration while preserving global coherence and editability. In practice, these advances translate into more robust pipelines, versioned asset decks for game or film concepts, parameterized environments that designers can tweak in real time, and lighter weight tools for education and outreach. GAUGAN thus acts as a creative partner that speeds prototyping, supports rigorous evaluation, and invites systematic exploration of design choices while keeping the dialogue between human intent and machine output transparent and accelerating. Next, we switch gears to generative adversarial networks, the two-player setup where a generator tries to dream up images and a discriminator tests whether they look real. We'll see how GAUGAN lets you sketch a scene with simple labels, sky, trees, and water, and the model fills in textures, lighting, and details. You'll learn how semantic maps steer the creative process so you control layout while the machine handles the look. We'll discuss why this collaboration can produce diverse, high-quality visuals quickly, but also what can go wrong if training data is weak or the models are unstable. We'll preview practical workflows, from rough sketches to polished scenes, live editing, and quick concept art for games, films, and virtual worlds. Finally, we'll touch on performance, accessibility, and the trade-offs involved in real-time generation. Let me move beyond the basic two-network dual you've already heard about and focus on the engineering choices that make GANs robust, reliable, and actionable for researchers. First, stabilization techniques. Spectral normalization is now a standard tool for the discriminator. By constraining the spectral norm of each weight matrix, we effectively bound the Lipschitz constant. This reduces sensitivity to weight scaling, helps prevent exploding gradients, and leads to more predictable training dynamics. Alongside spectral norms, gradient penalties, most famously the WGAN-GP formulation, regularize the discriminator by penalizing deviations of the input-output gradient norm from 1. This tends to encourage smoother gradients and better coverage of the data distribution, which in turn supports more diverse, higher quality samples. Another practical lever is the update balance between generator and discriminator. The two-timescale update rule, or TTUR, prescribes different learning rates and update frequencies for the two networks. This avoids one network overwhelming the other and stabilizes training, especially in more challenging conditioning or multi-scale setups. Now, on architecture and conditioning. Beyond a single global discriminator, multi-scale discriminators help capture both global layout and fine texture, improving realism at multiple levels. Style-based generators, exemplified by StyleGAN concepts, offer finer control over texture and structure and can boost perceptual quality and editability. Conditioning plays a crucial role in many real-world tasks. GAUGAN-like systems demonstrate how semantic layouts guide generation to produce coherent scenes. This invites hybrid approaches such as combining conditional inputs with advanced generators to achieve controllable, high-fidelity outputs. Evaluation is essential and non-trivial. Frechet inception distance, or FID, remains a staple. It compares real and generated distributions in a learned feature space with lower values indicating closer alignment. The Frechet distance is complemented by kernel-based metrics like KID, which can be more robust in some regimes. Inception score has fallen out of favor for distributional quality, but perceptual metrics like LPIPS and structural measures such as MS-SSIM provide insight into perceptual similarity and diversity. It's good practice to pair objective metrics with human judgments and task-specific criteria, especially when deploying models for design or simulation. Finally, look to hybrids and future directions. Variational or auto-encoding elements, information maximizing variants, InfoGAN and diffusion GAN, hybrids blend strengths of different paradigms to improve sample quality, diversity, and controllability. In practice, success often comes from a careful combination. high-quality data with clear objectives, stabilized training via spectral normalization and gradient penalties, thoughtful architectural choices, and a robust evaluation plan. With these tools, GANs can reliably accelerate design, simulation, and creative exploration across domains. Semantic image synthesis gives us a controlled path from labeled ideas to photo-like scenes, but there's rich, ongoing work that sharpens both realism and reliability beyond the basic pipeline. A key thread is stabilizing and refining the generative process. Techniques like spectral normalization constrain the Lipschitz constant of the critic, helping adversarial training stay balanced as the model handles diverse semantic maps. Gradient penalties, including Wasserstein-style penalties, encourage smoother, more meaningful gradients and reduce mode collapse. Researchers also deploy multi-scale discriminators and perceptual losses that compare high-level feature representations rather than only pixel-level errors. The result is sharper textures, more coherent global structure, and better preservation of fine details across varying lighting and materials. Differentiable rendering and physics-informed losses are increasingly used to model shadows, reflections, and light transport, so the system can reason about illumination in a scene rather than merely colorifying regions. Evaluating these systems is itself an active area. In addition to traditional metrics like Frischeth inception distance for overall realism, practitioners use perceptual similarity measures such as LP-IPS to gauge how changes in texture or lighting affect human judgments. Semantic fidelity metrics matter too. One can compute the intersection over union IOU between a pre-trained segmentation network's output on the generated image and the input semantic map to quantify how well the layout and boundaries are preserved. Complementary metrics like SSIM or edge accuracy further capture structural alignment. Together, these metrics help diagnose whether the model is simply producing convincing textures or truly respecting the labeled scene structure. Hybrid and emerging models expand the design space. Conditional diffusion models, for example, can be guided by semantic maps to produce high-fidelity images with improved mode coverage and controllable detail. Diffusion GAN hybrids and score-based models combine the strength of diffusion's gradual refinement with adversarial feedback for sharper results. There is also work on incorporating scene graphs or relational reasoning, so the model understands not just where objects sit, but how they relate, e.g., tree next to path, car in front of building. Hybrid pipelines can blend traditional GAN components for speed with diffusion steps for quality, enabling practical editability in real-time or near real-time workflows. In practice, semantic inputs remain the anchor for layout and context. While these advanced techniques push realism, evaluation rigor, and reliable editing capabilities, the goal is to keep the user in control of layout while the model responsibly fills textures, lighting, and fine detail with high fidelity. In today's discussion, I want to unpack what makes GAUGAN's approach distinctive and what that means for researchers studying scene synthesis and interactive generation. First, GAUGAN marks a shift from unguided generation to guided synthesis by conditioning the image on a semantic map. Rather than starting from random noise, you delineate rough shapes and assign region labels: sky, water, trees, road, buildings, and so on. The segmentation map acts as a spatial prior that tells the generator where each feature belongs. You can place a river on the left and mountains on the right, and the system will fill in colors and textures that align with those labels. Crucially, the output updates in real time as you adjust the map, preserving coherence while you iterate, which makes composition experiments markedly more efficient. Second, this approach blends segmentation with deep generative modeling. It's not simply copying a style from a reference image. The model leverages the labeled layout to guide both the placement of objects and their appearance, drawing on learned priors for textures, colors, and lighting. By anchoring layout in the segmentation map and learning plausible region-specific appearances, GAUGAN can produce scenes that are structurally coherent and visually plausible rather than merely mimicking a single exemplar. Third, real-time interactivity is a core strength. Because updates are rapid, you experience an ongoing feedback loop. Tweak a label, move a boundary, or adjust lighting, and the scene responds immediately. This feels like directing a painter who understands your notes, enabling a dynamic exploration of hypotheses about composition, viewpoint, and illumination. For research workflows, this accelerates validation cycles and supports iterative testing of design hypotheses. Fourth, the quality and realism across a broad range of scenes are impressive since the system learns how regions interact under light and shadow. The model captures cross-region illumination, edge coherence, and texture transitions, reducing perceptual artifacts that can arise when boundaries are poorly defined. In many cases, a rough plan suffices to reach a polished render with minimal downstream editing. Fifth, accessibility and speed lower the barrier for experimentation. A compact set of labels can yield convincing, publishable quality results, enabling students and researchers to prototype complex layouts without specialized artistry. Next, we'll pull back the curtain on how this system is built and how the pieces fit together. We'll look at a modular blueprint where components snap together and how that makes it easy to swap or extend parts. You'll hear about conditioning inputs, labeling maps and user sketches that steer the generator and help place sky, road, and trees with the right lighting. We'll explain how residual blocks and the three core layer types keep information flowing smoothly, sharpening textures without breaking the model. Then we move to training, paired maps and photos, adversarial learning, and the trio of losses, adversarial, feature matching, perceptual that guide realism and semantic fidelity. Finally, we'll connect the dots to GAUGAN's workflow from map to photoreal image and preview practical uses and editing paths. Today, we examine the high-level architecture of the system with an eye toward practical realism and research-driven rigor. As a reminder, the core pairing remains a generator that converts maps and sketches into photorealistic imagery and a discriminator that judges realism. We keep the multi-scale and patch-based analysis to ensure both global coherence and fine-grained texture accuracy. Spade still drives texture alignment by injecting spatially adaptive normalization at multiple layers, preserving structure while enabling texture and style control from segmentation maps and user sketches. Beyond the basic layout, several stabilization and expressivity techniques are central to achieving robust, high-fidelity results. First, we employ spectral normalization on the discriminator's weights. By constraining the Lipschitz constant, we improve gradient flow and reduce training instability, especially as outputs reach high resolutions. In addition, gradient penalty regulation, such as an R1 divided by R2 penalty on real or fake gradients, or the WGAN GP approach, helps smooth the loss landscape and further mitigate mode collapse. These penalties complement the patchGAN locality, ensuring that both tiny textures and global scene structure are learned without brittle heuristics. On evaluation, we move beyond human judgment to quantitative metrics that enable rigorous comparison. The Freshet inception distance, or FID, remains a standard for measuring how close the generated distribution is to real images in a learned feature space. We also consider kernel inception distance, key for statistic robustness, and perceptual metrics like LPAPS to capture perceptual similarity rather than just pixel-wise error. For high-resolution outputs, we examine metrics across scales and, when possible, apply task-specific evaluations such as downstream editing, consistency, or user study confidence activities that align with the intended design workflow. Architecturally, the system can benefit from hybrid modeling and attention mechanisms. A post-GAN refinement stage, think a diffusion-based or refinement network, can polish residual artifacts and complex light interactions without sacrificing the generator speed. Self-attention or cross-attention modules can improve long-range coherence when objects interact across the scene, complementing Spade's local texture control. We can also layer perceptual losses A, Z, VGG-based features, or style losses to better align color, lighting, and material properties with real references. In practice, this combination, spectral normalization, gradient penalties, robust evaluation, and hybrid refiners supports a stable training regime, reliable quality metrics, and a flexible, artist-friendly workflow. The result remains two collaborators on one canvas, the generator proposing plausible scenes with texture fidelity, and the discriminator guiding refinements to push toward photorealism. Now, I want to take you a bit deeper into how the design choices we've discussed actually pay off in practice, especially when you're pushing GAUGAN-like systems toward real-world tasks. The core message remains: modularity, conditioning, and stable learning enable rapid adaptation and robust results. But we can sharpen this with a few advanced tools and metrics that researchers use to push quality and reliability. Starting with the modular design, Think of the system as a set of clean, interchangeable bricks. This isn't just code hygiene, it supports principled experimentation. You can swap backbones, swap upsampling strategies, or replace the normalization and activation schemes without rewriting the whole pipeline. In addition to speed and debugging benefits, modularity makes it straightforward to explore hybrids or enhancements, for example, integrating a diffusion-based refinement module or a perceptual loss block as a plugin, while preserving the conditioning and residual flow that carry semantic structure through the network. Conditioning inputs remain central to steering the output. Semantic maps, as you know, provide a rich, scene-structured guide. Beyond simple maps, you can explore context-aware feature modulation, such as adaptive normalization techniques that condition the features on the semantic map. This helps the generator allocate resources where the scene demands detailed sky versus foliage, water reflections, or texture granularity, leading to more realistic lighting, texture, and spatial coherence. On the stability side, more advanced training controls are now common in high-fidelity synthesis. Spectral normalization constrains the spectral norm of discriminator weights, stabilizing adversarial training by preventing runaway gains that destabilize gradients. Gradient penalties, as in WGA-NGP, enforce Lipschitz continuity more directly, smoothing the optimization landscape and reducing mode collapse tendencies in conditional setups. These techniques complement the residual blocks and the layered building blocks, convolution, normalization, activation, to help gradients flow and the network learn deeper, more nuanced representations without sacrificing stability. Evaluation also needs to be precise and multifaceted. Fresheth inception distance, or FID, remains a go-to metric for quantifying realism of generated distributions, but it should be used alongside other measures, KID for kernel-based similarity, LPPS, for perceptual differences, and task-specific metrics such as semantic consistency scores. In practice, you'll report a small suite of metrics that reflect both fidelity to the data distribution and fidelity to the conditioning maps. Finally, hybrid models are a natural frontier for this modular design. A clean interface lets you experiment with integrating diffusion refiners, learn post-processing, or multi-stage discriminators without losing the advantages of your conditioning pathway and residual structure. In short, the combination of modularity, conditioning, stability tricks, and rigorous evaluation creates a flexible, scalable framework for advancing high-quality, context-aware image synthesis in real-world research settings. Today, I'll outline how a maps to photographs pipeline advances beyond the basics by integrating stability techniques, richer losses, and robust evaluation. The core idea remains: a generator G learns to translate a semantic label map into a photorealistic image guided by a discriminator D that judges realism. The conditioning on label maps enforces semantic structure, while adversarial feedback drives texture and rendering details. To push training stability and fidelity, we adopt several architectural and regularization tweaks. First, spectral normalization on the discriminator helps bound its Lipschitz constant, reducing gradient explosions and producing steadier updates as the generator refines high-frequency textures. In tandem, gradient penalties, as used in WGAN-GP, enforce a soft Lipschitz constraint across training, which often yields crisper edges and more reliable convergence in complex street scenes with diverse materials. Beyond stability, loss design becomes richer. Adversarial loss remains central, but we pair it with feature matching loss to stabilize learning by encouraging the generator to match intermediate discriminator features rather than chasing the final binary decision alone. Perceptual loss, computed on high-level features from a pre-trained network, guides the output toward human-perceived realism rather than pixel-perfect similarity, particularly for textures such as foliage, asphalt, and glass. Crucially, a semantic consistency loss can enforce alignment between the input map and the produced image, ensuring labeled regions, sky, road, buildings, cars appear in the correct locations and with plausible appearances. Architecturally, we often employ multiple discriminators. A patch-based multi-scale discriminator focuses on local texture fidelity, while a global discriminator ensures consistency of the overall scene layout. Attention mechanisms can help the model allocate resources to difficult regions, such as occlusions or complex lighting, preserving structural fidelity while improving realism. Evaluation now includes dedicated metrics. Fresheth inception distance measures the similarity between the distribution of generated images and real photographs, capturing both quality and diversity. LPIPS assesses perceptual similarity, aligning more closely with human judgments than pixel error alone. Semantic metrics such as the IOU between a segmentation of the generated image and the input map quantify semantic fidelity. Human perceptual studies can complement these quantitative measures for a holistic evaluation. Hybrid approaches also enrich this space. Some workflows combine GANs with diffusion refiners or leverage coarse to fine synthesis to capture both global layout and fine textures. Hybrid models can offer improved stability and controllability, enabling rapid exploration of layouts for travel scenes or design concepts. The takeaway is clear. By integrating spectral normalization, gradient penalties, richer loss terms, multi-scale discriminators, and robust evaluation, a maps to images framework becomes not only more realistic but also more reliable for research and creative exploration. Next, we move from pixel labels to shaping an image with a simple sketch. Semantic maps act as roadmaps, telling the computer where sky sits, where roads belong, and how textures should feel. You'll see a sketch input interface that lets you draw regions, tag them with labels, and paint colors so the generator understands your plan. The workflow is 3 steps. Sketch the rough layout, assign class labels to each region, and apply colors for clarity. Then, when you generate, the model fills in textures and lighting while keeping edges and spatial relationships consistent. Because changes affect only the marked parts, you can iterate quickly. We'll also touch collaboration, saving layouts, and real-world uses in games, film, design, and education, showing how this approach helps craft believable worlds and clear storytelling. Advancing from the basic idea that a semantic map guides a generator, we can dive into the architectural and training techniques that make high-quality, controllable image synthesis practical in research settings. The core idea remains: the map provides structure, but we must ensure the model fills that structure with realistic textures, boundaries, and details without tearing or breaking the layout. A key stabilization tool is spectral normalization applied to the discriminator. By constraining the spectral norm of weight matrices, we bound the Lipschitz constant and prevent the discriminator from becoming too confident too quickly, which helps avoid aggressive gradient updates that can destabilize training. Complementing this, gradient penalties such as the WGAN-GP formulation enforce smoothness in the critics function space. Together, these techniques improve convergence when conditioning on dense semantic maps, where a misaligned texture could easily violate spatial semantics. On the generator side, conditioning mechanisms have evolved beyond simply concatenating a map with latent vectors. Spatially adaptive normalization, or SPADE, modulates normalization layers using the semantic map at every spatial location. This allows the generator to preserve sharp class boundaries and align textures with the intended classes. Roads stay textured like asphalt, skies remain airy, foliage stays leafy. The result is more faithful scene structure and more natural transitions between regions. Discriminator design also matters. Multi-scale discriminators, including patch-GAN style critics, enforce realism at both fine-grained textures and global layout. This helps the model respect local details, edges, textures, while maintaining coherent large-scale geometry, building placement, road networks. Regularizers and auxiliary losses such as perceptual losses that compare high-level features from a pre-trained network further align generated content with human perceptual judgment. Evaluation has become more nuanced. In addition to traditional FID, fresh at inception distance for overall realism, researchers track LPIPS for perceptual similarity and, when possible, inception score. For semantic condition synthesis, it's informative to measure how well downstream tasks perform on generated images e.g. running a pre-trained segmentation model on the output to see if the semantic boundaries remain intact. Some groups report pixel accuracies or mean intersection over union on generated images as a proxy for structural fidelity. Hybrid models are another fruitful direction. Combining GANs with diffusion models or using diffusion steps to refine a semantic map-guided initialization can yield sharper textures and more controllable style transfer while retaining the semantic integrity imposed by the map. These hybrids often balance the fast generation of GANs with the sample quality of diffusion methods. In practice, the take-home is that semantic maps empower not just what is drawn, but how it is drawn. By leveraging normalization condition generators, SPADE, stable critics, spectral norm, GP, and robust evaluation, FID LPIPS task-based metrics, we can push semantic guided synthesis from plausible to truly reliable and deployable in research pipelines. Now, we're going to discuss about an interactive sketch-to-image interface that lets you draw regions and assign labels and colors to build semantic layouts. The core idea is straightforward, but the power comes from how you encode and leverage that layout to condition the generator, and how you evaluate and refine the result. From a modeling perspective, the sketch, the per region labels, and the color codings become a spatial conditioning map. Typically, this is represented as a semantic map with one hot channels per class aligned to the output resolution. The generator then uses this map to guide decoders, attention modules, and skip connections. So each region contributes its own texture, lighting cues, and geometry. This enables precise control over layout and composition while preserving global coherence. You can extend the interface by adding more regions to capture finer details such as shadows, reflections, or distant objects, and you can refine boundaries by nudging labels or colors. On the training side, several advanced techniques improve stability and quality in this conditioning regime. Discriminators can be designed with a global and a multi-scale local component to ensure both overall realism and regional fidelity. Stabilization often relies on spectral normalization to control the Lipschitz constant of the discriminator and gradient penalties as in WGAN GP to enforce smooth, well-behaved gradients during training. As you iterate, you can pair GAN-based objectives with perceptual losses or style losses to preserve textures in regions, while enforcing edge-aware losses to sharpen boundaries between adjacent classes. Beyond GANs, diffusion models offer a compelling hybrid path for this task. A semantic layout can condition a diffusion process, yielding high-fidelity, texture-rich results with improved mode coverage. Hybrid approaches GANs for fast iterations plus diffusion refinement for final renders can deliver both speed and realism. When you need speed in a classroom or workshop, lightweight distillation or guided sampling can bring diffusion quality outputs closer to real time. Evaluation is essential to study how well layout changes translate into image changes. Traditional metrics like FID quantify realism relative to real images, while IS, KID, and LPAPS provide complementary views of diversity and perceptual similarity. In layout condition generation, you can also measure layout consistency metrics, how well the produced image aligns with labeled regions or with boundary sharpness. Human-in-the-loop studies offer valuable insights into interpretability and usability, particularly when students compare layouts by swapping labels or moving regions. Ultimately, this interface turns creative sketching into a measurable synthesis pipeline. It supports collaboration, reproducibility, and rapid experimentation. Save layouts, reuse them across projects, and let peers review the plans before generating images. Today, I want to expand how semantic segmentation functions as a precise control layer in image generation rather than just a labeling step. Think of it as drawing the anatomy of a scene. We mark where each object begins and ends, and we link those boundaries to the image's texture and lighting transitions. This matters because crisp, well-placed boundaries help texture changes, fur, glass, fabric to feel intentional rather than abrupt or jarring. When regions are well-defined, features stay coherent across the whole frame, which supports a natural, believable result rather than a patchwork of inconsistent details. A key strength of this approach is establishing the relationships between objects. By specifying where one object sits relative to another, say, a cat beside a mat, you anchor the scene's spatial logic. That guidance helps maintain consistent shadows, reflections, and color relationships as the composition evolves. The outcome is not only more realistic, but also easier for audiences to trust and interpret. For artists, this input becomes a powerful tool. It lets you shape layout with confidence while preserving your established style. From a practical workflow perspective, you can break the process into 3 steps. First, define which objects exist in the frame. Second, place each object in its intended position. Third, specify their relative sizes. Beyond placement, you can prescribe textures, rough fur, smooth glass, wrinkled fabric, so the system propagates those material cues coherently across all affected regions. Semantic guidance also helps keep lighting and shadow steady as you experiment with arrangements. If you adjust the layout, the system reshapes only the marked parts, leaving the rest intact. This non-destructive behavior saves time and preserves the artist's original intent. The analogy of a coloring book with smart lines is useful here. You draw the lines where you want changes, and the computer fill in the textures and lighting that align with those lines. For students, think of segmentation as a roadmap for a scene. You tell the system where each character or object should sit. Then the system fills in textures and lighting accordingly. Change a line, and the rest remains consistent, which accelerates comparison across design variants. In practice, segmentation supports workflows in games, films, product design, and educational visuals. It enables rapid iteration of styles and layouts without starting from scratch. You'll notice subtle shifts, edge, sharpness, and transition fidelity as objects move. Remember, segmentation is a tool, not a magic button. Skillful use comes from practice, informed adjustment, and a clear narrative intent. Mastery means you guide machines to help rather than boss them around, yielding a final image that is a deliberate blend of plan and technique. Next, we'll step behind the curtain of GAUGAN's generator. We'll trace how a sketch or segmentation map becomes a believable image through a multi-scale backbone that reads the scene at different levels of detail. We'll explore residual blocks that keep earlier features alive, and adaptive normalization that adjusts textures to the layout using spatially adaptive normalization. Think of it as a guide that paints with semantic awareness, letting sky, trees, water keep their places even as style shifts. We'll then watch how upsampling lifts the image step by step, balancing speed and quality, and how boundary-aware filters protect edges so borders stay crisp. Finally, we'll see how the system refines color and texture across scales to produce coherent, high-fidelity results. This mix yields images that feel both faithful to the map and richly realistic. Today, we delve deeper into the generator architecture at the heart of GAUGAN and connect its design to training, dynamics, synthesis, quality, and evaluation. The generator turns segmentation maps into realistic images, but the strength of GAUGAN lies in its multi-scale design, which explicitly targets both coarse layout and fine texture. At a high level, this arrangement allows the model to capture structure across spatial frequencies, broad scene layout at lower resolutions, and detailed appearance at higher resolutions. The multi-scale pathway also supports faster convergence, because early stages establish the global arrangement while later stages refine details, reducing the burden on any single layer to produce everything at once. Residual blocks sit at the core of the architecture, enabling smooth information flow through deep networks. The shortcuts bypassing several layers help preserve early features and gradients, mitigating vanishing gradient issues as resolution grows. This is especially important when combined with adaptive normalization, which we'll discuss next, because stable feature scaling across scales is essential for coherent texture synthesis. Adaptive normalization, and in particular SPADE, are what tie the image synthesis to the semantic map. SPADE injects segmentation information into the generator's normalization step so that the statistical parameters guiding feature scaling are conditioned on spatial semantics. Think of it as a painter who adjusts color and texture not globally but block by block according to the semantic guide. This yields images where textures, edges, and textures align with roads, trees, and buildings in the segmentation map, preserving spatial structure even as details become realistic. Beyond the standard architecture, there are stabilization and quality enhancement techniques worth highlighting. Spectral normalization, often applied to the discriminator, but increasingly adopted in generator modules as well, helps constrain the Lipschitz constant of learned mappings. This reduces sensitivity to extreme activations and helps prevent training instabilities and mode collapse across scales. Gradient penalties, such as the WGAN GP formulation, provide an explicit regularization of the discriminator's gradient, further stabilizing adversarial training and encouraging smoother transitions in generated content. When combined with feature matching losses or perceptual losses computed on VGG-like networks, the generator is nudged toward producing images whose intermediate representations resemble real ones, not just fooling the discriminator. Evaluation of these systems benefits from modern metrics. Frey inception distance and kernel inception distance key quantify distributional similarity to real images, while perceptual similarity metrics like LPIPS assess texture and detail fidelity. In segmentation to image tasks, researchers also look at semantic consistency metrics and, when possible, human judgments to capture perceptual realism. Hybrid approaches are another frontier. One can pair GAUGAN's semantic conditioning with diffusion-based refinements or with two-stage pipelines, where a coarse GAUGAN output is polished by a refinement network or a discrete latent code model. Such hybrids aim to combine the best of fast, structured generation with the expressive power of diffusion or autoregressive priors. Today, I'll expand on Spade's role in GAUGAN, focusing on how this conditioning mechanism interfaces with modern training practices, evaluation, and extensions beyond the basic idea. We start from the premise that Spade doesn't simply normalize features, it injects spatial semantic information directly into the generator at multiple scales via segmentation-guided normalization parameters. In practice, the segmentation mask is fed through a small network that produces spatially varying gamma and beta, which rescale and shift the feature maps. This preserves where things belong, sky, water, mountains, while still allowing the network to determine texture, lighting, and shading. The result is a faithful, controllable synthesis that respects layout constraints even as style and appearance vary. From a training perspective, several advanced considerations help Spade scale to high-fidelity results. First, stabilization. Discriminator stability remains critical in conditional setups. Many implementations employ spectral normalization on the discriminator to bound its Lipschitz constant, reducing gradient explosion and producing crisper, more reliable guidance to the generator. Gradient penalties, such as a WGAN GP or R1 penalty, can further encourage smooth, informative gradients, mitigating mode collapse and helping the network learn sharper boundaries between semantic regions. Together, these techniques complement Spade's semantic conditioning by enabling the generator to exploit the layout without oscillating during training. Turning to evaluation, advancing beyond visual inspection is essential for researchers. Standard realism metrics like FID provide a global measure of distributional similarity to real images, with lower FID indicating more realistic outputs. Perceptual similarity metrics such as LPI/PS quantify how much perceptual appearance changes across samples. For layout-guided synthesis, semantic fidelity metrics add another layer. Compute a segmentation map for generated images with a pre-trained head and compare it to the input layout using mean IOU or per pixel accuracy. This directly tests whether the generated content respects the labeled regions. Reported results should include both realism and semantic consistency indicators to give a complete picture of performance. There are also exciting hybrid and extension directions. Spade concepts can be integrated into diffusion models, where semantic maps guide denoising steps to yield sharp, semantically coherent images while benefiting from diffusion's robust diversity. Hybrid losses that combine adversarial objectives with perceptual or style consistency terms can further enhance both fidelity and controllability. Finally, practical extensions, multi-scale conditioning, style variation within a layout, and boundary refinement enable richer, more diverse results without sacrificing structural correctness. In GAUGAN, Spade provides a reliable bridge between your sketch or mask and the final paint. When paired with stable optimization practices, robust evaluation, and thoughtful extensions, it becomes not just a normalization trick, but a versatile framework for controllable, high-quality image synthesis. I'm happy to discuss specific metrics or integration strategies for your own projects. Let me take you through how output images are formed in modern generative systems, focusing on what happens under the hood as the image is built up. The generator doesn't deliver a single pass of pixels, it refines and amplifies structure across scales. This is multi-scale feature synthesis in practice. Features at coarse, middle, and fine resolutions inform each other, with information flowing through skip connections and progressively detailed blocks. In implementation terms, you often see a coarse to fine multi-scale layout, where each level contributes textures, edges, and context, while a coordinating loss or discriminator provides supervision at multiple resolutions. This approach typically uses multi-scale discriminators to ensure realism at every scale, helping the model avoid oversmoothing or scale-specific artifacts. Next, consider edge, sharpness, and transitions. Edges matter. Our visual system is highly sensitive to borders between objects. The network employs boundary-aware strategies to protect these borders as refinement proceeds. This includes losses and filters that emphasize gradient, consistency, and edge fidelity, along with techniques like gradient penalties, for example, WGAN-GP, and spectral normalization to stabilize training and keep the discriminator's feedback well behaved across scales. Edge-aware upsampling and carefully designed gradient-based losses help ensure that textures do not smear at object boundaries, particularly in cluttered scenes with occlusion and depth variation. Color and texture refinement come next in the pipeline. Progressive refinement sees colors and patterns cohere across the whole image, while lighting and shading are harmonized across surfaces. Here, we increasingly rely on context-aware conditional normalization schemes. Spatially adaptive normalization, famously embodied in spade-like approaches, conditions, color and texture on spatial structure, semantic maps, layout guides, or scene priors. So skin, metal, water, and fabric maintain believable, scene-consistent appearances as refinement proceeds. Perceptual losses and feature space consistency checks often accompany these to preserve realism beyond pixel accuracy. To evaluate and push progress, researchers use metrics such as freshet inception distance (FID) and its counterpart skeet, plus perceptual metrics like LP-IPS and precision divided by recall for distributions. These help quantify both fidelity and diversity, and they guide architecture or loss function choices when comparing multi-scale or edge-preserving variants. Hybrid approaches are also emerging, combining GANs with diffusion-inspired refinement, or injecting perceptual and energy-based priors into the training loop to stabilize learning and widen the space of plausible images. In short, three guiding ideas drive modern high-fidelity generation: synthesize across multiple scales, protect edges and borders during refinement, and refine color and texture with context-aware normalization and perceptual coherence. Together, these enable lifelike images from rough plans with broad applicability in games, cinema, and design, and they support rapid exploration, changing lighting or mood with small, interpretable edits while preserving global coherence. Alright, think of the discriminator as the stern but fair critic in a speed draw contest. We've seen how it guides the generator by feedback that sharpens realism. But there's more to the stage. Multi-scale discriminators bring two lenses, close-up texture and wide structure, so the model learns both fine details and overall harmony. Using multiple views makes feedback stronger and training steadier, helping avoid mode collapse and giving richer signals for updates. Then we pair the adversarial game with extra tools, feature matching, and perceptual losses that keep textures believable while preserving semantic meaning. Balancing these losses matters. Too much adversarial pressure can distort edges, too little can dull details. In practice, a sketch becomes a photo-like image, step by step. Next, we'll see how these ideas apply in real projects and what designers should watch for in loss design. Let me push this idea a bit further and connect the role of the discriminator to the stability and quality of modern image synthesis. The intuition remains. The discriminator is the critic guiding the generator toward realism. But today, we also rely on two kinds of leverage to make that guidance constructive rather than destabilizing. First, stability through regularization of the critic. Spectral normalization is a practical tool that constrains the Lipschitz constant of the discriminator. By normalizing the weight matrices spectral norms, D can provide well-behaved, bounded gradients to the generator across training, which reduces sharp jumps in the generator's updates and helps prevent oscillations or divergence. This is especially valuable when you scale up networks or work with high-resolution images where uncontrolled gradients can derail learning. Second, gradient penalties and alternative losses. The gradient penalty idea, popularized by WGAN GP, enforces a soft one Lipschitz constraint by penalizing deviations of the gradient norm from one along interpolations between real and fake samples. The effect is to smooth the discriminator's decision boundary in the regions the generator traverses, yielding more informative and reliable gradients for G, even when the real vs fake signal is weak. Beyond WGNGP, hinge loss and other discriminative losses can also sharpen the boundary in a way that stabilizes training and often improves sample quality. Third, richer feedback signals and conditioning. Discriminators are not limited to binary real divided by fake judgments. Projection discriminators and auxiliary classifiers can inject class condition or attribute condition feedback, encouraging the generator to respect semantic structure. Relativistic discriminators, where D estimates the probability that real samples are more realistic than fake ones rather than absolute realism, have also shown benefits in some settings by focusing the generator on relative quality. These architectures enable more nuanced guidance without sacrificing the core adversarial dynamic. Fourth, evaluation and monitoring. In practice, we rely on metrics that quantify both realism and diversity. Freshet inception distance and its skin provide distributional alignment signals, while precision recall formulations for generative models help separate fidelity from coverage. It is crucial to pair these with qualitative checks and, when possible, human judgments, because a single metric can mislead if mode collapse or overfitting masquerades as high quality. Fifth, hybrid approaches. You'll often see GANs paired with encoders, VA GAN, BiGAN, or multiscale discriminators that operate at different resolutions to capture both global structure and fine textures. These hybrids leverage the discriminator's evaluative power while borrowing strengths from complementary models to improve both realism and diversity. In short, the discriminator remains a critical, honest referee, but with spectral normalization, gradient penalties, richer losses, sophisticated evaluation, and thoughtful hybrids, we push toward not just fooling the judge but achieving truly trustworthy, high-fidelity image synthesis. Let me take the idea of multiscale discriminators a step further and talk about practical design choices and the modern toolkit researchers use to make these systems robust and evaluable. First, architecture and fusion. In practice, you build a pyramid of discriminators, each attending to a different spatial resolution and receptive field. A small-scale critic scrutinizes texture and fine-grained patterns, while a large-scale critic enforces global structure and coherence. The challenge is how to combine their feedback. Common approaches include summing the scale-specific losses with learned or fixed weights, or feeding the per-scale judgments into a lightweight metacritic that produces a single supervision signal. A popular variant uses a shared backbone that extracts multiscale features with separate heads for each scale. This reduces parameter redundancy while preserving specialization. Second, stabilization techniques. The GAN literature offers several complementary tools to keep training stable across scales. Spectral normalization applied to discriminators helps constrain the Lipschitz constant, which is especially valuable when you have several discriminators operating at different resolutions. This tends to smooth gradients and prevent one scale from dominating learning dynamics. Gradient penalties, as in WGAN-GP, can be employed per scale or on the aggregated discriminator output. Per-scale penalties are attractive when data density varies across scales. They help maintain balanced gradients and faster convergence. In practice, many teams use a combination: spectral normalization for a solid baseline, plus a light gradient penalty to fine-tune stability during the early training phases or when introducing a new scale. Third, evaluation and diagnostic metrics. Beyond qualitative checks, you want robust metrics that reflect both realism and diversity. Freshet inception distance FID remains a workhorse for overall realism, but multi-scale contexts benefit from complementary probes. Per scale or multi-resolution FID variants, computing FID on downsampled crops or on different scales can reveal where the model preserves texture versus structure. Freshet video distance FVD is relevant for temporal data. Complement with KID kernel-based and precision divided by recall for generative models to quantify mode coverage versus quality. Practically, report a suite of scores and provide scale-wise diagnostics to show that each level contributes meaningfully. Fourth, hybrid or extended models. Multi-scale discriminators pair well with patch-GAN style discriminators, which focus on local realism, and with perceptual or style losses that inject high-level texture constraints. You can also integrate energy-based components or auxiliary tasks A, G, semantic consistency losses to anchor global layout, while the multi-scale critics refine details. When combining penalties and scales, tune the loss weights carefully. Imbalanced emphasis can skew the generator toward satisfying some scales at the expense of others, reducing diversity. Finally, apply this to domains like fashion imagery or architectural scenes. The multi-scale view ensures tiny thread work and broad silhouette are both credible, improving realism and robustness. In short, multi-scale discriminators, when paired with normalization, penalties, thoughtful fusion, and strong evaluation, offer a concrete path to stable, high-fidelity GANs that generalize across data regimes. Let's pick up from the adversarial tug-of-war and focus on what makes training both stable and genuinely useful in research settings. Even with a strong adversarial signal, GANs can wander or oscillate. To tame that and push toward reliable realism, We bring in stability-centric penalties and carefully chosen auxiliary losses, all of which collaborate with the core adversarial objective. One family of stabilization techniques targets the discriminator's behavior. Spectral normalization constrains the Lipschitz constant of the discriminator by rescaling weight matrices, yielding more predictable gradients and better generalization across tasks. Complementarily, gradient penalties, most famously the WGA and GP term, explicitly encourage the gradient norm of the discriminator with respect to inputs to stay near 1. These penalties mitigate mode collapse and overly aggressive updates, especially in high resolution or high variance domains. In some regimes, R1 or R2 regularization on real or fake samples is also used to dampen sharp fluctuations. Taken together, these methods keep the competing networks in check without dampening the power of the adversarial signal. Beyond stability, auxiliary losses shape what realistic means in practice. Feature matching loss computes differences between intermediate representations, not just pixel values, across layers. So the generator aims for coherent textures and structures like skin, hair, and lighting patterns without chasing every pixel. Perceptual loss, the high-level semantic distance in pre-trained feature spaces, helps preserve shapes and relationships that are important to human judgment. Recently, LPIPS and related perceptual metrics provide more nuanced guidance than simple L2 pixel losses. The key is to balance these auxiliary objectives with the adversarial drive, so we preserve semantic fidelity and texture without introducing blur or drift from the target distribution. Evaluation is essential for research progress. Freshet inception distance FID is the workhorse. It compares the statistics of real and generated features, offering a quantitative sense of realism and diversity. Kernel inception distance, KID, and perceptual similarity measures AG provide complementary views. Precision recall metrics for generative models illuminate how well the model covers the real data distribution versus generating artifacts. When reporting results, it's prudent to couple these metrics with qualitative assessments and ablations to trace which losses contribute most to the observed gains. Hybrid models illustrate the landscape of possibilities, combining GAN objectives with diffusion steps, autoencoder reconstructions, or style-based generators as in StyleGAN to leverage complementary strengths. In practice, one often tunes a dynamic weighting scheme that adapts during training, enabling adversarial pressure to remain strong while auxiliary and regularization terms guide stability and content preservation. In short, adversarial realism, stabilized optimization, and consistency across conditions form a powerful triad. As you advance, monitor both objective values and human judgments, and consider spectral normalization, gradient penalties, and careful auxiliary objective design as essential tools in your research toolkit. As we move past the section header, let's step into GAUGAN's creative rhythm. You'll see how starting with the semantic sketch lets you choreograph a scene, sky, water, land, trees, so the computer fills in the texture while you focus on composition. What changes appear in real time, guiding lighting, mood, and balance. If the river feels still, a quick nudge on the flow direction will reshape the scene. Then we shift to the practical side, exporting high-resolution images in formats ready for posters or projects, or keeping flexibility with layered PSDs. We'll also preview the user-friendly workspace, drag-and-drop tools, context menus, real-time previews, and smart presets that speeds experimentation. Finally, we glimpse real cases, artists, game developers, and educators using GAUGAN to prototype, collaborate, and teach with rapid feedback. Today, I want to unpack GAUGAN's workflow for building scenes, focusing on 3 linked activities: sketching semantic layouts, real-time refinement, and straightforward export. This is not about teaching you the basics of GANs, but about how the interface encodes intent, how the model responds to iterative edits, and how researchers can evaluate and extend the pipeline. First, sketch semantic layouts to control composition. You mark regions such as sky, water, land, and trees. The goal is rough segmentation, not finished artwork. The regions act as conditioning signals that guide texture placement, lighting, and depth. For a river sunset landscape, you'd sketch the bright sky, the river path, the river bank, and distant hills, and you can annotate light and shadow zones to steer illumination. Beyond intuition, this is where advanced stability mechanisms come into play. A modern conditional generator benefits from spectral normalization to constrain the discriminator and stabilize learning under changing layouts. Gradient penalties, as in WGA and GP, help preserve texture fidelity when the user makes sharp boundary edits. And a patch-based discriminator enforces local realism along region borders, producing seamless transitions between sky and water or land and trees. There is also value in a semantic-aware loss that encourages physically plausible interactions, causal depth ordering, shading consistency, and coherent occlusions, so rough cues yield plausible global structure. Second, real-time feedback and refinement. The core advantage is immediate visual updates as you tweak flow direction, texture scale, color, or brightness. This fast loop supports rapid exploration of mood and composition and makes bold ideas feasible without restarting from scratch. From a research viewpoint, it enables data collection on how users sculpt scenes, and it invites system-level refinements such as latent space edits or per-region controls. Evaluation metrics come into play here. Free-shade inception distance not tracks realism against a reference corpus. LPAPS captures perceptual similarity to desired appearances, and diversity metrics monitor variety across edits. Third, exporting and downstream use. High-resolution images can be saved in PNG, JPEG, TIFF, or layered formats for further editing. The semantic map itself remains a reusable scaffold for iterations or for driving other tools in a design pipeline. To push fidelity further, many workflows couple GAUGAN style generation with hybrid models, diffusion, or super resolution post-processing, targeted in-painting, or style divided by color grading, so you retain user control while achieving photorealistic detail. In short, sketch, refine, export, and when needed, augment with post-processing to realize publication-ready scenes. This three-step rhythm, augmented with stability techniques, quantitative evaluation, and compatible post-processing, makes GAUGAN a powerful partner for art, design, and storytelling in research contexts. Today, we turn to what makes this image tool genuinely approachable for researchers and students alike. The focus is not only on what the software can do, but on how its design sustains rigorous work without getting in the way of curiosity and discovery. First, the user interface is engineered to shorten the path from idea to image. You can assemble components with drag and drop, which mirrors natural tinkering rather than forced sequencing. Real-time previews keep your sense of how a change will look before you commit, so you can evaluate color, contrast, and composition on the fly. Context-sensitive menus appear when you need them, reducing needless clicks and keeping the workspace uncluttered. In practice, this means you learn by experimentation, not by memorizing a long handbook, and you can prototype hypotheses with minimal friction. Second, customization is deliberately powerful yet approachable. Sliders give you intuitive control over style and texture, making it easy to push a concept toward a particular aesthetic. Presets provide ready-made directions, sketchy outlines, watercolor washes, or other traditional looks that you can adopt with a single click and then fine-tune. The ability to adjust texture, brightness, and edge definition lets you tailor the image to your research narrative, whether you're illustrating a data visualization, a concept diagram, or a visual abstract. This balance of presets and granular control supports both rapid ideation and careful refinement. Third, integration with NVIDIA Studio and Omniverse expands collaborative and rendering capabilities across platforms. Real-time collaboration enables teammates to edit together, whether you're in the same room or distributed across campuses. Advanced rendering accelerates the production of believable visuals, which is particularly valuable for presenting complex ideas. AI-driven content generation can suggest textures or shapes to spark new directions, while still allowing you to guide the creative process and maintain methodological integrity. All of this sits in a single, unified interface, so you spend less time hunting for tools and more time working with ideas. GAUGAN's promises with real-world practice, highlighting three concrete use cases: art and design, game development, and professional content creation, and what they reveal about how this technology accelerates work, oasis of creativity. I'll broaden this with some advanced angles researchers care about without returning to basics. First, artists and designers. GAUGAN already feels instantaneous, turning rough sketches into plausible landscapes with textures that read as photorealistic at a glance. Behind that immediacy lies stability and quality controls that matter in scholarly work. Modern implementations benefit from stabilization techniques such as spectral normalization in the discriminator, which helps maintain consistent gradients as styles shift. Gradient penalties used in WGAN GP frameworks further curb instability during training when you push toward diverse textures and lighting conditions. Perceptual losses can preserve high-frequency details, think fine brushwork in skies or rock faces, without forcing exact pixel matches. When teams evaluate results, they rely on objective metrics like free shade inception distance to quantify realism relative to real images, complemented by LPI-PS for perceptual similarity. Yet, they also depend on user studies and expert ratings to capture subtleties that metrics miss. The workflow becomes a blend of quantitative checks and qualitative judgment, ensuring the sketches evolve into images that satisfy both artistic intent and perceptual realism. Second, game developers. GAUGAN accelerates environment prototyping, enabling rapid edits to rooms, terrains, and lighting during design sessions. For production pipelines, this sits alongside considerations of latency and consistency across engines. Here, hybrid approaches shine. Pairing GAUGAN-like semantic to image pathways with diffusion-based refinements can yield sharper shadows, more convincing atmospherics, and better global illumination cues. Lightweight distillation and model compression support real-time feedback, preserving interactivity while maintaining fidelity. Non-destructive editing and version canvases help teams track stylistic choices, textures, moods, and lighting across iterations. From a research vantage, this is a prime setting to study style transfer stability under domain shifts and to quantify how well generated assets generalize to in-engine rendering. Third, professional content creators. The ability to switch styles to align with brands or campaigns while retaining consistent composition is invaluable. Real-time feedback supports rapid style transfer experiments, and hybrid models can offer higher fidelity outputs suitable for client reviews. In practice, evaluation again leans on FID and perceptual metrics, augmented by human evaluations of brand alignment and mood accuracy. The non-destructive editable outputs encourage iterative refinement and collaboration, which is crucial for fast turnaround projects and cross-disciplinary workflows. Across all cases, several patterns emerge. A simple sketch can be guided toward realism with controlled variation, collaboration, and iterative evaluation. GAUGAN lowers barriers to art-based work, enabling experimentation without starting from scratch, while still valuing hands-on drawing for foundational skills. And as with any tool, its best use is as a partner that accelerates ideas into compelling images, not a wholesale replacement for traditional craft. Before we dive deeper, think of GAUGAN as a creative partner that turns rough sketches into convincing images. It shines in three areas: photorealistic texture and lighting, interactive control that lets you shape mood with simple sliders, and fast feedback you can see on common hardware. As we move on, we'll compare the strengths with the real-world limits the next slides discuss. Expect three main challenges: rendering fine detail in dense scenes, dependence on clear input, and limited texture variety that can feel repetitive. We'll also cover practical fixes, careful planning and precise labeling, testing textures early, and sometimes blending GAUGAN with manual edits for precision. Finally, we'll preview ongoing improvements, better upsampling, broader semantic labels, and domain adaptation to generalize across subjects and lighting. The message: use GAUGAN as a starting point, guided by careful testing and iteration. GAUGAN exemplifies how modern generative models translate sketch-like intent into convincing visuals, but to use it effectively in research and production, we need to go beyond the surface strengths. Today, I'll outline advanced angles that matter to researchers and designers alike: stabilization and realism, controllable semantics, and real-time practicality, with a view to evaluation and integration into workflows. First, photorealistic detail. The heart of GAUGAN's realism lies in how per-pixel conditioning and high-fidelity texture synthesis align to lighting cues and material priors. From a research perspective, stability and fidelity hinge on techniques such as spectral normalization on discriminators, and, where applicable, generator control via gradient penalties to enforce Lipschitz continuity. These choices reduce mode collapse and improve texture consistency across large, complex scenes. In practice, multiscale discriminators and perceptual losses further sharpen fine-grained details, edges, foliage, and water textures while maintaining global coherence. For semantic alignment, spade-style conditioning injects segmentation maps into normalization layers, ensuring textures correspond to scene semantics. When evaluating realism, Fréchet inception distance and its variance, along with LPIPS perceptual similarity, provide objective metrics, complemented by human studies to capture mood and lighting quality that numbers alone miss. Hybrid rendering ideas using neural textures and differentiable rendering to fine-tune rough materials and global illumination can push realism without sacrificing speed. Second, flexible control for diverse creative testers. GAUGAN's strength here comes from explicit scene control. Semantic maps guide where trees, rocks, or water appear. Sliders and inputs modulate textures, weather, sky color, and object presence. From a research angle, this invites exploration of latent space semantics, invertibility, and interactive editing pipelines. Advances include semantic guided style modulation, texture aware normalization, and material presets that preserve physical plausibility under edits. Hybrid models can couple neural rendering with lightweight physically based constraints to ensure that a changed sky or wet surface still obeys plausible lighting falloff. In practice, this means designers can sculpt a scene with rough shapes and progressively refine through targeted texture and lighting layers, all while maintaining realism and coherence. Third, speed and efficiency for real-time workflows. Inference speed on commodity hardware remains a priority. Techniques such as model quantization, FP16 divided by INT8, pruning, and tensor accelerated runtimes e.g. TensorRT can yield real-time or near real-time performance without sacrificing perceptual quality. Efficient tiling, caching of frequent texture styles, and lightweight discriminators help maintain interactive frame rates. Importantly, these optimizations enable rapid iteration in game-level design, film concept art, and classroom demonstrations, where feedback loops are central to the creative process. GAUGAN gives us a remarkably intuitive handle on scene synthesis, but we should treat its limitations as invitations to sharpen our methods and evaluation. Let me outline how we can push beyond the three core constraints you see here: rendering detail in dense scenes, dependence on input quality, and limited texture variety. For researchers, the path is a blend of stabilized training, richer conditioning, and more robust evaluation. First, rendering fine detail in complex compositions. The challenge isn't just more pixels, but preserving high-frequency structure without introducing artifacts. To address this, we can deploy multi-scale architectures that synthesize at coarse and fine resolutions in a coordinated way. Think hierarchical generators paired with patch-based discriminators, and modern take on PatchGAN that attend to texture-rich regions. Stabilization techniques matter. Spectral normalization on discriminators constrains gradient magnitudes, while gradient penalties, as in WGAN-GP, encourage Lipschitz continuity and steadier learning. Pair these with perceptual or feature modality losses that operate in pre-trained networks feature spaces, so the model respects perceptual similarity alongside pixel accuracy. A diffusion-inspired refinement stage or a hybrid GAN diffusion loop can be used post-generation to enhance high-frequency detail without destabilizing the overall structure. Finally, incorporate attention mechanisms and global local conditioning so the model can allocate bandwidth to dense textures, metal, fabric, wood without washing out the rest of the scene. Evaluation should complement these ideas. Use Freshet inception distance and kernel inception distance, key for realism, LP-EPS for perceptual similarity, and targeted texture-based metrics to quantify material realism across scales. Second, input dependence and labeling robustness. When inputs are vague or mislabeled, results degrade. Strengthen conditioning by coupling semantic maps with uncertainty estimates and auxiliary losses that penalize inconsistencies between neighboring labels. Use domain adaptation techniques to close the gap between synthetic and real inputs and active learning loops to improve labeling where the model is uncertain. Consider probabilistic conditioning. Represent scene elements with distributions rather than fixed labels. Thus, the generator learns to hedge against ambiguity. For hybrid models, allow a controllable refinement path. The initial GAUGAN output can be fed into a diffusion or autoregressive upscaler that respects the original semantics while offering alternative, higher fidelity renderings. Third, texture variety and material richness. Repetition of surfaces erodes realism, especially for metals, woods, and fabrics. Address this with diversity-promoting strategies, stochastic texture sampling, multiple texture banks, and style condition decoding that blends material codes rather than repeating a single texture. Use differentiable texture synthesis and procedural texture modules to inject variety, along with discriminators that are sensitive to material consistency across objects. Spectral normalization, coupled with a texture-focused loss, helps avoid mode collapse into a narrow set of materials. 3 practical takeaways. Plan the scene with a clear semantic budget and iterative refinement. Label inputs precisely and verify them yearly. Test and diversify textures at early stages. Treat generated images as drafts, not final proofs, and use GAUGAN as a springboard for manual refinement and hybrid workflows. This mindset keeps us honest about limits while leveraging the tool's strengths to explore design space with rigor. GAUGAN already shows that turning rough, label-based prompts into polished images is within reach. Today, I'd like to build on that and sketch a path toward sharper detail, richer texture, smarter labeling, and stronger domain generalization. We'll also touch on how we measure progress and how hybrid models can push quality further without sacrificing practicality. First, let's tackle fine detail and high resolution. Even when a scene looks plausible, small textures, fabric weave, skin pores, micro patterns tend to blur at larger scales. A productive direction is to combine stronger upsampling with texture refinement that acts at multiple scales. Practically, that means employing multi-scale discriminators and loss terms that incentivize detailed preservation at each resolution. We can stabilize training with spectral normalization on the discriminator to bound its Lipschitz constant, and we can apply gradient penalties as in WGAN GP to reduce instability when learning high-frequency structures. On the generator side, perceptual or feature modality losses grounded in deep network activations help edges stay sharp and textures stay faithful. Advanced upsampling such as learnable anti-aliased upsampling, subpixel convolution, or progressive growing with refinement blocks can maintain edge clarity as resolution climbs. Finally, texture-aware losses and texture discriminators can encourage more convincing micro patterns, with evaluation guided by perceptual metrics like LP-IPS and FID to quantify realism beyond pixel accuracy. Second, expanding semantic label sets is powerful but costly. Richer conditioning allows the model to parse scene structure more precisely, but it also demands smarter architectural choices and data strategies. We can leverage hierarchical conditioning, coarse scene labels guiding the global layout, with fine-grained instance or part-level labels injecting detail where it matters. Techniques such as adaptive instance normalization (ADIN) or conditional batch normalization can inject label information more flexibly. Attention-based conditioning helps the generator allocate resources where semantic cues are strongest. To mitigate data demands, we can employ semi-supervised learning, label smoothing, and curriculum-style training, start with simpler label configurations, and progressively introduce more complex panoptic or instance-level maps as data allows. Third, generalization to new domains remains a central challenge. Domain randomization, exposing the model to wide varied variations in texture, lighting, and color during training, helps it ignore irrelevant differences. Complement this with domain adaptation methods, adversarial domain alignment, Corel divided by MMD objectives, to align feature spaces across domains. Broad, diverse datasets also improve robustness, and we should monitor cross-domain performance with domain-specific FID divided by LP-APS comparisons, not just standard metrics. Finally, how do we know we are progressing? Beyond FID and LP-APS, we should use task-relevant evaluations, including human judgments for perceptual realism and domain-specific criteria. Hybrid models combining GANs with diffusion refiners or vector-quantized autoencoders as a coarse-to-fine scaffold can deliver faster iterations with high fidelity. In short, better upsampling, smarter labeling, principled regularization, robust evaluation, and thoughtful model hybrids can push GAUGAN from impressive demonstrations toward reliable, real-world tools across fashion, design, and science without sacrificing the speed researchers need. As we turn to the next slides, we'll see GAUGAN in motion across creative and industrial settings. The tool isn't just turning sketches into lifelike scenes, it speeds up concepting, testing, and storytelling. We'll glimpse how designers in gaming sketch a mountain range and watch it become a photoreal landscape, then tweak weather, lighting, or seasons in real time. Real-time collaboration opens the door for teams to co-create, remix styles, and balance colors across disciplines from classrooms to studios. We'll explore how educators use it to illustrate topics without heavy setup, and how studios use it to prototype virtual sets for film and animation, cutting costs and timelines. Then we'll unpack the tech briefly, GANs, NLP, and reinforcement learning, and how they harmonize to turn words and sketches into coherent visuals. Finally, we'll outline the future, broader cross-domain use, richer control, and a human-centered blend of tools with your own voice preserved. GAUGAN opens a powerful creative channel. It lets artists move from a simple sketch to a lifelike scene, and in doing so, it invites new kinds of exploration. But beneath the immediate wow, there are important advances that shape how researchers design, evaluate, and deploy these systems in serious work. First, stability and fidelity matter at scale. Spectral normalization is now a standard tool for stabilizing discriminators, constraining their Lipschitz constant, and preventing aggressive gradient updates that can derail training. When the discriminator behaves, the generator learns more reliable mappings from rough layouts to convincing textures and lighting, yielding crisper sky captures, more believable foliage, and better edge definitions in architectural renderings. Complementing this, gradient penalties such as the WGAN-GP approach enforce smooth, meaningful gradients across the network. This reduces mode collapse and helps the model maintain coherent structure across large, detailed scenes, even when the input sketches are sparse or stylistically diverse. Evaluating the realism and utility of GAUGAN outputs goes beyond intuition. Frechet inception distance, or FID, remains a robust metric for comparing the distribution of generated images to real photographs, but it must be interpreted with care in domain-constrained tasks like semantic to photosynthesis. Perceptual metrics such as LPAPS quantify how close a generated image is to a reference in a human-perceived feature space, while task-focused metrics like color harmony, shadow consistency, and edge precision within regions can provide actionable feedback for iterative improvement. In practice, researchers pair objective metrics with user studies to capture the nuanced judgments of artists and designers. Hybrid modeling offers a compelling path forward. A common pattern is a two-stage pipeline. A semantic GAN establishes layout, composition, and broad lighting, followed by a diffusion-based refinement that adds high-frequency detail and photorealistic texture while preserving semantic agreement. Hybrid systems also enable creative control. You can steer overall mood with global style weights and then inject regional controls to adjust color temperature or contrast in specific objects or regions, maintaining physical plausibility. Real-time collaboration expands the reach of GAUGAN from a single author to a design studio, classroom, or remote artist collective. Multi-user canvases, live AI-assisted suggestions, and shared style pools enable co-creation with versioning and provenance tracking to maintain reproducibility. The AI assistant can propose tonal balances, balance cross-style blends, and maintain consistent lighting across collaborators' inputs, accelerating workflows without erasing individual voice. In education and industry, these tools democratize experimentation, yet we must respect originality and attribution. As we advance, the conversation moves from replacement to augmentation. The human touch remains central, but with smarter, more controllable tools. Researchers and practitioners can coordinate ideas with AI more smoothly and responsibly. Today, I want to move beyond the surface capabilities and examine how GAUGAN achieves its impact with attention to stability, evaluation, and deployment in real-world research workflows. The core value is not just look at pretty images, but the combination of fidelity, controllability, and speed that enables rapid experimentation across domains from game design to virtual production. From a technical perspective, producing photorealistic, semantically guided scenes at interactive rates requires careful attention to model stability and generalization. Practical GAUGAN-style systems typically rely on strong regularization and normalization strategies. Spectral normalization is often employed in the discriminator to constrain its Lipschitz constant, reducing the risk of unstable gradients during training. Complementary gradient penalties, such as WGAN-GP, enforce smooth gradient behavior with respect to the conditioning inputs, improving robustness when the semantic layouts are edited or perturbed in real time. These choices matter not only for training stability, but also for the quality and reliability of on-the-fly edits that users expect in production or research environments. Evaluation in this space is multi-layered. Traditional metrics like the Frechet inception distance that provide a global sense of realism and diversity across generated scenes. But researchers increasingly pair FID with perceptual metrics such as LPAPS to capture human-aligned similarity and with semantic consistency measures to ensure that layout edits translate into faithful, spatially coherent changes. For researchers, coupling objective metrics with user studies on task performance in design review, for example, helps quantify the value of real-time feedback loops, hybrid evaluation pipelines, including ablations on normalization, loss terms, and conditioning strength, are essential for understanding trade-offs between fidelity, controllability, and speed. Hybrid modeling approaches offer a path forward for balancing speed and quality. In practice, conditional GANs can be augmented with diffusion-based refinements or lightweight post-networks to polish textures after an initial fast render, enabling a two-tier pipeline, a rapid coarse synthesis followed by a higher fidelity pass. VQVA style encodings can compress complex scenes for streaming in VR with a decoder that preserves spatial coherence under dynamic lighting and weather changes. These hybrids are particularly appealing for cross-domain work. A single train model can support gaming, AR divided by VR training, and architectural visualization with domain adaptive fine-tuning. Finally, deployment considerations matter. Real-time generation benefits from model pruning, quantization, and hardware-accelerated inference to maintain low latency. Spatial tiling and progressive refinement allow large scenes to load incrementally, preserving interactivity as players or trainees move through virtual spaces. GAUGAN stands at the forefront of AI-driven image synthesis. Its architecture is not just about fast rendering, it embodies a principled approach to turning core sketches and label maps into photorealistic scenes, and it serves as a proving ground for ideas that cut across vision, rendering, and human-computer interaction. From a technical vantage, the stability and fidelity of GAUGAN derive from a family of regularization and normalization strategies. Spectral normalization is commonly employed in the discriminator to constrain the Lipschitz constant, which helps prevent the kind of unstable gradients that plague high-fidelity synthesis. Gradient penalties, such as the WGAN-GP formulation, enforce a soft Lipschitz condition on the generator-discriminator pairing, smoothing the training dynamics when the semantic conditioning is rich and multimodal. In practice, practitioners layer multiple discriminators, operating at different scales to capture both global layout and fine-grained texture, and may include path length regularization to ensure that changes in the latent or sketch space produce consistent perceptual changes in output. Collectively, these tools elevate the reliability of the generator as a creative instrument and enable more controllable, interpretable synthesis. Evaluation also evolves beyond visual inspection. The Fréchet inception distance, or FID, provides a quantitative measure of how close the generated distribution is to the real data distribution, while the KID and LPAPS metrics offer complementary views on perceptual similarity and texture fidelity. Together, they give researchers a calibrated sense of progress and generalization. In parallel, ablation studies and human judgments remain important for capturing aspects that metrics miss, such as compositional correctness or lighting coherence under varying conditions. Hybrid modeling is a fertile area here. One can imagine integrating diffusion-inspired refinements with the spatially conditional GAN core so that the semantic map guides a coarse-to-fine synthesis while diffusion steps polish global illumination and atmosphere. Neural rendering acts as a differentiable bridge from abstract scene representations to photoreal shading, enabling end-to-end optimization that respects geometry, light transport, and material cues. In practice, such hybrids retain real-time interactivity for design tasks while gradually extending fidelity and controllability. From an application perspective, GAUGAN's value lies in its interoperability, with NLP to translate descriptions into features, with reinforcement learning to adapt to user feedback, and with cross-domain tools like architectural simulators. The result is faster prototyping, better visualization, and more expressive creative tools. For researchers, GAUGAN remains a compelling sandbox to probe semantic image synthesis, evaluation regimes, and the integration of perceptual quality with interactive control. Today's wrap-up distills the deck into a compact map for future work. We revisited 10 takeaways: understand the problem clearly, simple questions yield powerful answers, explain ideas with real examples, connect new ideas to what you already know, test with small experiments, stay curious about the unknown, measurements matter even when simple, share ideas for critique, be patient as complex problems unfold, document what you learn so you can build on it. Looking ahead, the future brings tools, simulations, lightweight software, friendly datasets that let us see how small changes ripple through a system. We'll emphasize accessibility, clear diagrams and visuals, classroom discussion and collaboration, ethical thinking with safety, accuracy, and fairness at the center. Progress is incremental, every student can contribute. The journey continues beyond this slide. Now we are going to discuss about GAUGAN beyond the sketch to photo pipeline and focus on three architectural pillars that make it both fast and faithful. SPADE, a multi-scale generator, and the discriminator. These elements work together to translate simple layouts into rich, believable scenes while keeping you in the driver's seat. First, SPADE normalization. SPADE stands for Spatially Adaptive Normalization, and in plain terms, it modulates how features are scaled and shifted at every layer based on the semantic map you provide. Instead of blindly normalizing everywhere, the network learns to produce gamma and beta maps from the layout and applies them region by region. The result is that color, texture, and illumination stay tightly coupled to the scene's shapes, grass, looks, where the map says grass, sky stays smooth above, rocks acquire rugged edges where you drew them. This spatially adaptive gating is applied throughout the network, preserving fine layout details even as the image goes through many refinement stages. It's a powerful way to inject strong prior knowledge about structure while leaving the actual texture synthesis to the generator. Second, the multi-scale generator. Rather than a single monolithic pass, GAUGAN builds the image in a coarse-to-fine sequence. A low-resolution stream establishes global composition, lighting, and rough textures. Successive, higher-resolution stages add edges, micro-textures, and depth cues. Think of it as sculpting. Rough forms first, then polishing with increasingly fine detail. This pyramid structure helps the model manage both large-scale regions, expanses of sky or water, and tiny textures, pebbles, foliage, reflections without one compromising the other. To aid realism, there is often conditioning of multiple scales, along with architectural features like skip connections that propagate structural information upward and help ensure consistency across resolutions. Third, the discriminator. The critic evaluates realism and alignment with the sketch, acting as a counterweight to the generator. Modern GAUGAN setups often employ multi-scale or patch discriminators to judge both global plausibility and local fidelity. Stabilizing techniques are essential. Spectral normalization constrains the discriminator's Lipschitz constant. Gradient penalties, such as R1 or WGAN-GP style terms, improve training stability and reduce artifacts. In practice, the discriminator guides the system to place colors, textures, and edges in ways that look photorealistic to human eyes while remaining faithful to the semantic map. For evaluation and iteration, researchers now rely on metrics like freshet inception distance and KAD to quantify realism along with LPAPS for perceptual similarity. Hybrid approaches are also worth noting. Integrating diffusion-inspired refinements or diffusion-GAN hybrids can push realism further while maintaining the controllability afforded by SPADE-based conditioning. Today, we imagine where AI image generation is headed. The running themes are realism and variety, but the story is fuller when we add training stability, richer control, and true multimodality in a single image. Realism is evolving beyond surface cosmetics to convincing lighting, texture, depth cues, and perspective consistency. In practice, that means models learn to render shadows, specular highlights, and occlusion in a way that passes human judgment under varied viewing conditions. The question isn't only does it look real, but does it behave like a scene under change, camera angle, lighting, or motion cues? 1. To gauge progress responsibly, we rely on robust evaluation, freshet inception distance and its skin, along with perceptual metrics like LPIPS and, when appropriate, KID. FID correlates with perceptual quality at scale, but it's imperfect and sensitive to dataset and feature choices, so researchers often pair it with human studies and task-specific metrics. As realism improves, we must also assess diversity, controllability, and consistency across frames in sequences or multi-view prompts. Training stability remains a central lever for efficiency. Techniques such as spectral normalization constrain the discriminator's Lipschitz constant, reducing fragile dynamics and mode collapse. Gradient penalties, as in WGAN-GP, promote smoother, more meaningful gradients that guide the generator toward higher fidelity samples. These architectural and objective tweaks enable fewer training runs to reach useful quality, which translates into lower compute and broader accessibility, especially in academic labs and classrooms. In addition, hybrid strategies combining the strengths of GANs with diffusion-style sampling or score-based refinements promise rapid, sharp outputs with controllable attributes, offering faster iteration without sacrificing fidelity. Multimodal synthesis is moving from single prompts to orchestrated inputs. You might fuse text, rough sketches, reference images, or even scene-level constraints like lighting direction. Attention mechanisms and clip-guided guidance help align generations with high-level intents while preserving local detail. Real-time interaction lets designers see updates as they adjust prompts or sketches, a boon for rapid prototyping in design studios and education. GAUGAN-like systems illustrate the impact. Rapid prototyping of landscapes, characters, and environments lowers barriers for beginners while giving experts a sandbox for exploration. The ripple effects touch advertising, game design, education, and industrial design, accelerating iteration cycles and broadening who can participate in creativity. As we push forward, responsible use remains essential. We need robust critique, traceability, watermarking, and bias mitigation. In research and teaching, we should study how these tools learn from data, test ideas with controlled projects, and cultivate a mindset that blends artistic inquiry with rigorous evaluation. Let's unpack how GAUGAN and its peers demonstrate a deeper set of ideas about creativity with AI beyond the surface of draw rough, get realism. The story here isn't only about faster sketch to photo, it's about stability, controllability, and credible evaluation ingredients researchers rely on when we push these systems toward real-world use. First, think about training stability and fidelity. Modern GANs benefit from techniques like spectral normalization, which constrains the discriminator's Lipschitz constant. This keeps optimization well-behaved and helps the generator produce consistent detail across a wide range of inputs. Complementing that, gradient penalties, as in WGAN GP, encourage smoother, more meaningful gradients. Together, these regularizations reduce mode collapse and blur, enabling GAUGAN-like models to better generalize from coarse semantic maps to high-fidelity outputs while maintaining responsiveness. Second, the way we measure progress has become more sophisticated. The Fréchet inception distance, or FID, provides a quantitative proxy for realism by comparing generated and real image distributions in a learned feature space. But FID isn't the whole story. Perceptual metrics such as LPI PS gauge perceptual similarity to reference images, while precision divided by recall variance of GAN evaluation reflect both quality and diversity of generations. Researchers increasingly pair these with human studies to capture usability and alignment with domain goals because a realistic image isn't automatically useful if it misses the intended semantics or creative constraints. Third, the architecture and training recipe have evolved toward hybrid and multi-stage approaches. GAUGAN's strength lies in conditioning on semantic layouts. Advanced workflows blend this with hierarchical discriminators and perceptual losses to preserve structure while delivering photorealistic textures. Looking forward, hybrid models that couple GAN-like speed with diffusion model fidelity are especially promising. Use a fast, rough draft generator to propose a scene, then refine with diffusion-based modules that enforce sharpness and global consistency. Such hybrids can offer both interactivity and high realism, expanding the practical toolbox for designers and scientists. On the user side, real-time feedback remains crucial. Techniques like progressive upsampling, tiling, or model-accelerated inference enable interactive preview while keeping visual quality high. This matters for education, planning, and design reviews, where quick iterations accelerate insight without sacrificing rigor. This notebook shows how deep learning can turn simple sketches into realistic landscapes. With just a few strokes, a drawing can become a forest, a lake, or a city scene filled with natural details that look real. This project is not only about code, it's about giving people a new way to create. Instead of spending hours on careful work, an artist or designer can start with a quick outline, and the model fills in textures, lighting, and details. This makes the creative process faster, easier, and often more exciting. GAUGAN works because it has learned from millions of real images. It understands the look of trees, water, skies, and buildings and can combine them to form new scenes. The result is a tool that doesn't replace creativity but supports it, helping people turn ideas into pictures more quickly than ever. This section begins by importing the essential PyTorch libraries needed for building neural networks, including the core torch library, the neural network module, and functional operations. Following the imports, a custom class called Spade is defined, which inherits from NN module, indicating that it is a neural network layer. The Spade class is designed to incorporate spatially adaptive normalization, which is particularly useful in tasks like semantic image synthesis. It takes two key arguments during initialization: the number of channels in the input feature map and the number of channels in the conditional input, such as semantic labels. Inside the constructor, a batch normalization layer is created to normalize the input features across the batch, ensuring stability during training. Next, a sequential module called self Spade is set up, which consists of few convolutional layers. The first convolution takes the conditional input with its number of channels and maps it to the same number of channels as the input features. It is followed by a ReLU activation to introduce nonlinearity. Then another convolution increases the number of channels to twice the original, preparing for the split into gamma and beta parameters, which will be used to modulate the normalized features. In the forward method, the input feature map X is first normalized using the batch normalization layer. The conditional input seg, which contains semantic labels, is resized to match the spatial dimensions of X using nearest neighbor interpolation. The process seg is then passed through the Spade convolutional network, and its output is split into two parts along the channel dimension, gamma and beta. These parameters are later used to perform spatially adaptive normalization, effectively allowing the model to incorporate semantic information at each spatial location during image generation. This code defines a class called residual block, which inherits from PyTorch's NN module, indicating that it represents a neural network layer. The purpose of this block is to implement a residual connection, a common technique in deep learning that helps mitigate the vanishing gradient problem and allows for training deeper networks more effectively. The constructor of this class takes three parameters: in channels, which specifies the number of input feature channels, out channels, indicating the number of output channels, and con channels, which refers to the number of channels in the conditional input used within the Spade normalization layers. Inside the constructor, the code determines the smaller of the input and output channels, assigning these to hid channels. This value is used to define the intermediate number of channels within the block, ensuring compatibility between layers. The code then checks whether the input and output channels differ. If they do, a projection is necessary to match the dimensions for the residual connection. In this case, it initializes a Spade normalization layer called norm0 and a 1x1 convolution, con0, with spectral normalization to stabilize training. This projection ensures that the residual connection can be added correctly even when the number of channels changes. Next, the code defines a leaky ReLU activation function, which introduces nonlinearity with a small slope for negative inputs, helping prevent dying neurons. It also initializes two more Spade normalization layers, norm1 and norm2, for the main convolutional path, each condition on the respective number of channels. The first convolution, con1, maps from in channels to hid channels using a 3x3 kernel with padding to preserve spatial dimensions, and is spectrally normalized for stability. The second convolution, conv2, maps from hid channels to out channels, also with a 3x3 kernel and spectral normalization. Overall, this residual block class is designed to perform a residual operation with conditional normalization, allowing the network to adapt its feature scaling based on additional conditioning information, which is crucial for tasks like image synthesis, where context-aware normalization enhances the quality and coherence of generated images. This code defines an encoder class that inherits from the neural network module in PyTorch. The purpose of this class is to process input images and encode their features into a latent space representation. It takes several parameters: the spatial size of the input images, the dimensionality of the latent noise vector, the number of downsampling blocks, and the number of base channels in the initial convolutional layer. The class sets a maximum number of channels to 512 to prevent the network from becoming excessively large. In the constructor, it initializes an empty list to hold the layers and sets the initial number of channels to the provided base value. It then enters a loop that creates a series of convolutional blocks, each performing downsampling. Within each iteration, it determines the number of input and output channels, where the first layer takes 3 channels for RGB images and subsequent layers double the number of channels up to the maximum limit. Each block consists of a spectral normalized convolution for stability, followed by instance normalization and a leaky ReLU activation function to introduce nonlinearity. After constructing these layers, it calculates the spatial dimensions of the feature map after all downsampling steps by dividing the original height and width by 2 raised to the power of the number of downsampling layers. This prepares the encoder to process images efficiently while capturing hierarchical features. This code defines a class called generator, which is a core component of a generative adversarial network, specifically designed for creating images from random noise and class labels. The class inherits from NN module, making it compatible with PyTorch's neural network framework. Within the class, several parameters are specified, such as the number of object classes in the dataset, the spatial size of the generated images, the dimension of the noise vector, the number of channels in the last hidden layer, and the number of upsampling layers. These parameters allow the generator to be flexible and adaptable to different datasets and image resolutions. The constructor begins by calculating the spatial dimensions after downsampling based on the provided image size and the number of upsampling steps. It then projects the input noise vector Z into a high-dimensional tensor that can be reshaped into a feature map suitable for further processing. This is achieved through a linear layer followed by a reshape operation. Next, the generator employs an upsampling layer which doubles the spatial dimensions at each step and a list of residual blocks. These residual blocks are added in reverse order, starting from the smallest spatial scale, and they progressively refine the feature maps. Each residual block takes in a certain number of input channels and outputs a refined feature map with potentially different channel dimensions, controlled by the base channels and the current layer index. Finally, the generator includes a sequence of layers to produce the final image. This consists of a convolution layer that reduces the feature map to 3 color channels, corresponding to RGB, followed by a tan activation function to ensure the pixel values are scaled between -1 and 1. This design allows the generator to produce realistic color images conditioned on class labels, starting from a simple noise vector and progressively building up detailed features through upsampling and residual processing. This code defines a class called PatchGAN discriminator, which is a type of neural network module used as a discriminator in generative adversarial networks, specifically for PatchGAN architectures. The purpose of this discriminator is to evaluate the realism of small patches within an image rather than the entire image at once, which helps in capturing finer details. The class is initialized with parameters such as in channels, which specifies the number of input channels like 3 for RGB images, base channels, which determines the number of feature maps in the first convolutional layer, defaulting to 64, and n layers, indicating how many convolutional layers will be stacked with a default value of 3. Inside the constructor, it first calls the superclass constructor to set up the module properly. It then creates a list called layers, using NN, module lists. This list will hold all the layers of the network, and using module list allows us to easily access and output intermediate features, which can be useful for calculating losses at different scales. The first layer added to this list is a sequential block containing a convolutional layer wrapped with spectral normalization. This normalization stabilizes training by controlling the Lipschitz constant of the layer. This convolution takes the input with in channels and outputs base channels, feature maps, using a kernel size of 4, a stride of 2, and padding of 2 to reduce the spatial dimensions. Following this, a leaky ReLU activation with a negative slope of 0. 2 is applied, introducing nonlinearity. Next, the code prepares to add additional downsampling convolutional layers, which will further extract features while reducing the spatial size. A variable channels is initialized with the base channels, and a loop is set up to add these layers, but the snippet cuts off here, so the details of these subsequent layers aren't shown yet. Overall, this structure creates a flexible, multi-layer discriminator capable of analyzing image patches at different scales, which is essential for high-quality image synthesis. This code defines a class called discriminator, which is a crucial component in a generative adversarial network. The purpose of this class is to evaluate the realism of generated images, helping the model improve over time. Within the initializer, it takes several parameters: the number of input channels, which depends on the data, the base number of channels used in the network, the number of downsampling layers, and how many discriminators are used at different scales. The idea is to create multiple discriminators that analyze the input at various resolutions, enhancing the model's ability to detect fine details and global coherence. The core of the implementation is a list of these discriminators, each instantiated as a patch GAN discriminator, which focuses on local patches of the image to judge realism. These are stored in a module list, allowing PyTorch to properly register them as part of the model. To facilitate multi-scale analysis, a downsampling layer is defined using average pooling. This layer reduces the spatial dimensions of the input, so each subsequent discriminator receives a scaled-down version of the image, enabling the model to assess both fine and coarse features. In the forward pass, the input is processed sequentially through each discriminator. Before passing to each subsequent discriminator, the input is downsampled, except for the first one, which sees the original input. The outputs from all discriminators are collected, providing multiple evaluations of the input at different scales, which helps the overall model learn more robust and detailed representations. This code defines a class called GAUGAN, which inherits from PyTorch's NN module, indicating that it represents a neural network model. The class is designed to encapsulate the architecture of the GAUGAN model, which is used for generating realistic images from semantic layouts. Within the class, there's a detailed docstring that describes several key parameters. For example, in classes specifies the number of object categories in the dataset, while spatial size defines the dimensions of the output images as a tuple of height and width. The parameter base channels determines the number of channels in the initial layers of both the generator and discriminator, serving as a base for the network's capacity. The z-dim parameter sets the size of the noise vector, which introduces randomness into the generation process. Additionally, n-upsample indicates how many times the network performs downsampling and upsampling operations, effectively controlling the resolution and detail of the generated images. The n-disk layers parameter specifies the number of layers within each discriminator, and n-disk indicates how many discriminators are used at different scales to improve the realism and diversity of generated images. The constructor method init initializes these parameters and then calls the superclass constructor. It proceeds to instantiate an encoder which encodes input images or layouts into a latent representation, and a generator which synthesizes images conditioned on semantic labels and the encoded features. The encoder is configured with the spatial size of the images, the size of the noise vector, the number of downsampling steps, and the number of base channels. The generator is similarly configured with the number of classes, spatial size, noise dimension, base channels, and upsampling steps. This setup forms the core architecture of GAUGAN, combining encoding and generation processes to enable high-quality image synthesis from semantic inputs. In this section, we start by importing the models module from Torch Vision, which provides access to pre-trained convolutional neural network architectures. We then define a custom class called VGG19, which extends the base NN module class, allowing us to utilize the VGG19 model for feature extraction purposes. Within the constructor of this class, we load the pre-trained VGG19 model and extract its feature layers. We create 5 separate sequential modules, each corresponding to different segments of the VGG19 network, by slicing the original features at specific layer indices. These segments are designed to capture intermediate representations at various depths of the network. To ensure that the VGG19 model is used solely for feature extraction without updating its weights during training, we set all parameters to be non-trainable by disabling gradient computations. The forward method processes an input tensor through each of these feature segments in sequence. It computes the outputs at each stage, storing them as H1 through H5, which represent feature maps at different levels of abstraction. Finally, it returns a list of these feature maps, enabling downstream tasks such as perceptual loss calculations or style transfer that leverage intermediate representations from VGG19. The code begins by importing modules needed for handling user credentials and file operations. It then prompts the user to enter their Cityscape's username and password, with the password input being hidden for security. A new directory named data is created to organize the downloaded files. Next, the script uses a system command to perform a login to the Cityscape's dataset website. It sends the username and password via a post request, saving the session cookies to a file called cookies.txt. This setup allows subsequent requests to access protected data. After logging in, the code navigates into the data directory and downloads two packages from the Cityscape's website using the saved cookies to authenticate the request. These packages contain the images and ground truth annotations needed for training and evaluation. Finally, the code unzips the downloaded files within the data directory, extracting the image data and the corresponding ground truth annotations, preparing the dataset for further processing and model training. This section begins with importing essential libraries such as YOOS for operating system interactions, NumPy for numerical computations, and modules from Torch Vision, transforms for image transformations. It also imports the image class from the PIL library to handle image processing. Next, it defines a custom dataset class called Cityscape's dataset, which inherits from Torch. Utils. Data. Dataset. This class is designed to load and manage the Cityscape's dataset, commonly used for urban scene understanding. Within the class, the constructor initializes the dataset with a list of paths, a specified image size defaulting to 256 by 512 pixels, and the total number of object classes set to 35 by default. It stores the number of classes and prepares a dictionary to hold dataset examples. The constructor then checks whether the provided paths argument is a single string or a list. If it's a string, it loads examples from that directory. If it's a list, it iterates through each path and loads examples from each directory. If the argument is neither a string nor a list, it raises a value error, ensuring that the dataset is constructed from valid input. This setup allows flexible data loading, accommodating both individual directories and multiple dataset sources. In this section, we begin by importing the necessary modules to facilitate progress tracking and data loading. Specifically, we bring in TQDM for creating progress bars during training and data loader, from PyTorch to efficiently load our dataset in batches. Next, we define a function called .lr lambda. This function serves as a learning rate scheduler, adjusting the learning rate dynamically based on the current epoch. It returns a scaling factor that remains at 1 initially, but after a certain point specified by decay, after it linearly decreases the learning rate until the end of training, which is determined by the total number of epochs. We also define a weights init function which is responsible for initializing the weights of our neural network layers. It checks if a given module is either a convolutional layer or a linear layer, and if so, applies Xavier uniform initialization to their weights to promote better training stability. Moving on, we set up the device configuration to utilize a GPU if available for faster computation. Otherwise, we default to the CPU. We then define a configuration dictionary for our GAUGAN model, specifying parameters such as the number of classes, the spatial size of the input images, which is halved from the default to conserve memory, the number of base channels, the dimension of the latent vector, and the number of upsampling and discriminator layers. Using this configuration, we instantiate the GAUGAN model and transfer it to the selected device. We also initialize a loss function object, pausing in the device for proper computation. Finally, we prepare the data loading pipeline by specifying the directory containing our training data, setting a batch size of 16 smaller than the default to manage memory constraints, and creating an instance of our dataset class, Cityscape's dataset, which will handle loading and pre-processing the images for training. This section begins by importing two essential libraries for visualization and image processing. It imports Make Grid from Torch Vision, Utils, which is useful for creating a grid of images for easy visualization, and Matplotlib, PyPlot as .plt, which provides plotting capabilities. Next, the code checks the installed version of PyTorch by retrieving the version string and converting it into a tuple of integers, excluding the patch number. This is important because certain features, like autocast, or only available in specific versions. The code then sets a Boolean flag as autocast to indicate whether the current PyTorch version supports automatic mixed precision, specifically if the version is 1, 6 or higher. Following that, there's a function called notShowTensor images. This function takes a tensor of images as input, normalizes the pixel values from the range -1, 1 to 0, 1, and then prepares the tensor for visualization. It detaches the tensor from any computation graph, moves it to the CPU, and then creates a grid with a single image displayed. The image is then permuted to match the height, width, and color channels expected by matplotlib, and finally, it displays the image using PLT, imshow followed by PLT, to render the visualization. The last part of this section defines the beginning of a train function, which will handle the training process for the model. It accepts a data loader, the model itself, optimizers, schedulers, and the device on which to run computations. Inside, it unpacks the optimizers and schedulers for the generator and discriminator, initializes the current training step, and sets a display interval to control how often training progress is shown. It also initializes variables to track the mean losses for both the generator and discriminator during training. This setup prepares the ground for a training loop, which will be elaborated on in subsequent code cells. This notebook has shown how simple sketches can be turned into realistic, detailed images with the help of deep learning. What starts as a rough outline quickly grows into forests, lakes, or cityscapes, proof that artificial intelligence can act as a creative partner, not just a technical tool. We saw how neural networks can learn from huge amounts of images, picking up on patterns, textures, and styles. This ability allows the model to take even the simplest input and expand it into something far more complete and lifelike. It is a clear example of how machine learning can support human imagination. The lesson here goes beyond the code. GAUGAN points to a future where creating art and designs is faster, more accessible, and more experimental. Artists and non-artists alike can test ideas, visualize concepts, and bring scenes to life in ways that would otherwise take hours of manual work. At the same time, this raises new questions. What counts as original? Who owns AI-generated art? And how do humans and machines share creative roles? These are questions still unfolding, but they remind us that every new tool comes with both opportunities and responsibilities. As you move forward, I've already shared the code for this notebook in Teams. Please execute it on your end and let me know if you run into any issues. I'll be happy to guide you through.